Assalamu alaikum. It's our ninth lecture of Principal Methods and Applications of Nuclear Tracks. And in this lecture, we will discuss about the fission tracks. Okay, as we also you know that in previous lecture number 7 and 8 we discussed about the carbon dating. Here in this lecture number 9 we will supposed to discuss about the fission tracks dating. Okay, so what is basically fission tracks? So fission tracks first of all can be recognized by on the mica sheets. This is, let's suppose, mica sheets, and fission tracks can be detected on the mica sheets by these tracks, these lines. Okay, so on because it can be detected, so it makes fission fragments, and your fission tracks basically is a spontaneous reaction. Okay, it converts. Okay, and so that we can easily calculate the age. Okay, any age of that specimen, any specimen age we can calculate easily by the fission track dating. Okay, so basically fission track age are determined by three track densities. Okay, first of all is the rho s, which is the spontaneous track density, as I written here. Rho s, the formula of rho s is this, and the other thing is rho I, which we discuss further in our lecture, and the other factor is the rho d. These basically fission tracks ages are determined by these three track densities. Okay, you always remember rho s, the other is rho I, and the third one is the rho d. Okay, we will discuss each one of them briefly in this lecture. So for simplicity and clarity of presentation, we neglect for the present for the fact that the concentration of uranium 238 changes slowly. Okay, we know that with time, and half life of this is uranium 238 is basically 4.51 into 10 raised per 9 years. Okay, because you know that due to the alpha decay. So let's start first of all with the track density. You know that the first track density on which your fission track age are determined. So the first track density is basically the rho s, which is the spontaneous density, and your spontaneous track density is equals to a multiplies by lambda multiplies by n naught c 238 r 238 eta 238. Okay, these are the factors. So what are these factors? Basically rho s, as I told you, is basically the spontaneous track density, whereas a means time over spontaneous fission. Okay, whereas lambda is basically the decay rate of fission, and n naught is basically the number of atoms per unit volume, while C238 is basically the fraction of uranium 238 atom. Furthermore, R238 is basically the length of the etchable track. And finally, eta 238 is basically the etching efficiency. So these are the parameters of track density, specifically spontaneous track density. Okay, so there is a problem we have to solve to find the how we can find the spontaneous track density. So our problem is basically, and the problem is, consider we have measured the age of rock using uranium 238. Okay, using spontaneous track density technique, the information provided as the decay constant is lambda is equals to 8.46 into 10 raised to the minus 17 per year. Okay, these are the parameters which is initially given in our problem. Okay, so the first given is the decay constant lambda, and the lambda value is 8.46 into 10 raised to the minus 17 per year. Okay, whereas the time of the spontaneous fission is 1.5 into 10 raised to the minus 6, and you know that time basically is means that the value of a is given here. Okay, 1.5 into 10 to minus 60 minus 6 per year is basically the value of a time or spontaneous fission. and the number of atom per unit volume is 2.5 into 10 raised power 22. So this is the value of n naught, okay, number of atoms per unit volume. If the fraction of uranium 238 in natural uranium is 0.9927, so the fraction of uranium is given. So fraction of uranium atom is basically C238. So the value of C238 basically 0.9927, and the length of eachable track is 10 micrometers. So the length of eachable track is R238. So the value of R238 in our problem is 10 micro, means 10 into 10 raised to minus 6 meters. Understood? And the final thing is efficiency is also given, means eta, this eta 238, which is, that is the efficiency, and the value of efficiency in our problem is 0.85. But you have to find the spontaneous track density. So how you can find, the spontaneous track density with this relation, okay, rho s, which is equals to a lambda n naught c r eta. So let's find. What you have to do, you just have to put the values in this formula. You know that rho s is equals to a, and you know the value of a, as I told you, this 2.5, okay, sorry, this 1.5, okay, 1.5 into 10 raised to power minus 6, and the value of lambda, which is this, okay, this is basically the value and of lambda, which is 8.4, okay, 8.46 into 10 raised to minus 17, okay. Similarly, the value of n naught is basically this 2.5 into 10 raised to power 22, 2.5 into 10 raised to power 22, okay, multiplies by c r eta. The value of c is this 0.9927 multiplies by r. The value of r is this 10 micrometers. 10 into 10 raised to power minus 6 multiplies by 0.85, which is the value of eta. So after calculating, you will get your relation of rho s is equals to 2.5 into 10 raised to power minus 5, okay, but this is in what, this is basically atom, okay, per centimeter square dot year square. So to convert this year square into atoms per centimeter square, you have to multiply. So your rho s equals to 2.5 into 10 raised to power minus 5 multiplied by 1 year. You know that 1 year is basically has how much number of seconds, basically 3.15 into 10 raised to power 7 seconds in 1 year, okay, because square, so square, basically this cancels with this, so that's why we have to initialize this. After dividing this, okay, this over this, you will get your final answer, and your final answer is basically 2.5 into 10 raised to power minus 20 atom per centimeter square. So this is basically the final spontaneous track density. So this is how you can find. Okay. So we have another problem of this topic, which is spontaneous track density. So let's solve. So here is another problem, and the problem is the number of uranium 238 atom is given, which is 3 multiplies by 10 raised to power 22 atom per centimeter cube, whereas the fractional atom of C238, which is given 0.9927. If the length of the eachable track of uranium 238 fission fragments equals to 8 micrometer and the efficiency is 0.9, while the decay constant uranium 238 is 8.46 into 10 raised to the minus 7, okay, minus 17, sorry, per year, and the time of the spontaneous fission tracks and stored is 2 multiplied by 10 raised to the minus 6 per year. What you have to find? You have to find the track density of uranium 238. So you have to use the same procedure, same formula for the spontaneous track density. You know that basically equals to this, and all the values is given, like a time our spontaneous fission is given, and time of for the spontaneous emission is to multiply by this, okay, time of the spontaneous this 2 multiplies by 10 raised to minus 6 multiplied by lambda, which is, you know, that decay rate of fission, and decay rate is also given, which is, you know, here 8.46 into 10 raised to minus 17, okay, multiplies by n naught, and n naught is basically the number of atoms, and number of atoms is also given, which you know that here 3 multiplies by 10 raised to power 22, okay, atoms per centimeter cube. Another thing which is given is basically this r. The value of r is also given, which is this 0. Okay, here 0.9927, 0.9927, okay, and the value of this is the value of c basically, okay, and the value of r is basically 0.9, and the efficiency is also given, and this is the value of efficiency 0.9, and the value of r, which is the fission fragment, is given 8 micrometers, mean 8 into 10 raised to minus 6. So after calculating you will get your answer, and the answer is 3.62 into 10 raised to power minus 5. Again, this is in atom per centimeter square per year square, but you have to convert into atoms per centimeter square. So the answer is basically 3.64 into 10 raised to minus 20, okay, and atom per centimeter square. So this is basically the spontaneous track density, okay, this is how you can find. So now let's move on towards our second track density, and you know that our second track density is basically the induced track density. Induced track density. So you know that spontaneous track density is denoted by rho s, while your induced track density is denoted by rho of I. And the formula for rho of I means induced track density is basically equals to, which is this sigma phi, again Nu, okay, C235, R235, and eta 235, okay, whereas this sigma is basically the cross section, okay, and this phi is basically the thermal neutron per unit area, okay, so this is basically the thermal neutron per unit area. Okay, so this sigma is basically the cross section for inducing fission of uranium 235 in this case, because you know that in this case always 238 molecules are using, but in this molecules of uranium 238 is used, okay, so this sigma is basically the cross section for inducing fission of uranium 235, okay, with thermal neutrons. This phi means the thermal neutrons per unit area, okay, and the quantities in the second parenthesis are defined analogous to those as in the first. Okay, so these analogues are as same as we discussed in first, but here is 235, here 238. Okay, so this only changes. So this is how you can find the induced track density. Okay, and our final track density is basically, you know, that which is the, as I told you, is rho d. Okay, rho D. What is rho D is basically, this is basically to measure the neutron dose psi. Okay, this psi, neutron dose psi. So that's why we include with each group of samples to be neutron eradicated a piece of standard track detector. Okay, so that's why the density of fission includes in this glass. So rho D can be measured, is basically will be a measure of neutron dose. So this rho d can be written as rho d is basically equals to b psi. Okay, because as I told you, the density of fission induced in this class rho d will be a measure of neutron dose. Okay, so whereas the b is basically the constant. Okay, b here is basically the constant, is given formally by the expression. Okay, as you know that this is formally by the expression, this sigma n rd cd and eta d. Okay, this is same scenario as you see here. Okay, so b is basically the constant in this case, and all other aspects, this lambda is basically here convert is this sigma, and all other aspects c or eta as it is, and n is also as it is. So this b is basically means this value, and this value are constant quantities. Okay, defined for the dosimeter analogous to those equations as we discussed in here and here. Okay, whereas psi, you know that basically the thermal neutron per unit area. Understood? So this is how you can measure the rho d. Okay, now our final thing for this lecture, as the above equations can be combined, as we discussed, this equation and this equation can be combined to give the age in term of three trace densities. Okay, and a constant. So in term, so the age final is basically the age. After combining all these equations, we get the age in term of three track densities and constant, and the value of that age is basically equals to this by summation. Okay, multiplies by rho s divided by rho I. Okay, multiplies by rho d. Okay, this a is basically the age in terms of track densities. Understood? Whereas this summation sign basically equals to this again sigma c, because the ratio of spontaneous density by induced density. So you know that in spontaneous we take 238, so carbon 238 again R238 divided by eta 238 divided by the ratio with induced in track density, and you know that in induced we take 35, so C235 R235 eta 235, so again divided by B lambda here. So this is how you can find the age. Okay, the you can say you can say that the age in term of the three track densities. This is one track density, second track density, and third. So the age in term of three track densities can be written as this. Okay, and this is the value of constant. So this is all about. Okay, once this constant is known, three track densities counts basically allow the age to find the sample. Okay, you can easily find the age of any sample. Okay, and it must be age must be below than 10 raised power 8 years. Okay, old, you can say. So this is how you can find the age of any sample by knowing these constants, and the ratio age must be below than 10 raised power 8. If age is greater than 10 raised power 8, so you cannot find with this relation. So this relation is valid for calculating the age below than 10 raised power 8 years old. This is very high. Okay, so that's all for this lecture number 8 9 of principal methods and applications of nuclear tracks. So that's all for today. We will upload more lectures for this course, so stay tuned with us. Thanks for watching. Allah Hafiz.